Hello, everyone, and welcome to my talk on deep-born operator learning for reflection tomographic imaging. My name is Hassan Mansour, and I'm with Mitsubishi Electric Research Labs. This is joint work with our former intern, Qingqing Zhao from Stanford University, along with my colleagues, Yanting Ma, Saleh Nabi, and Petros Boufounos. Now, the task at hand is to try to recover the spatial distribution of the material permittivities that exist underground using only radar measurements. So what we do is we use a device that emits radar pulses into the ground. These radar pulses reflect off of objects on the ground and return to the receiver, which collects the data. So what we want to do is we want to use the received data along with the knowledge of the transmitted signal in order to estimate the material properties of the objects underground. General problem formulation for this problem is to assume that the received measurements are indicated or denoted by the vector y, and these are collected at the surface of the scene. And from the measurements y, we want to infer an image of the subsurface, which is similar to what we see inside the red box. And we do this by minimizing the difference between y and a measurement operator h that tells us where the receiver locations are found, which multiplies a forward model that relates the material permittivity f to the total wave field that exists within the ground as a result of the pulse that's emitted from the transmitting antenna. So we minimize the measurement mismatch y minus hz, and we add to that some form of regularization. And classically, we would have used total variation regularization for these types of images, or for these types of targets. Now, the problem with this type of formulation is that you need accurate knowledge of the forward model Z, which is fine in the case where you have a simple background, or for example, a homogeneous background, such as free space. However, once the background becomes complicated, then we do not have accurate knowledge of the physics of the wave propagation, which makes this problem significantly harder. So the current approaches use physics-based constraints, such as the Lippmann-Schwinger equation, which is which solves the integral form of Helmholtz equations that describe the wave propagation inside a material. The limitations of such approaches is that, first of all, we need to know exactly the background, and we need to formulate the Green's function corresponding to that background, which in itself is a difficult problem to formulate. And it requires us to know exactly what the background is, which we do not know in these realistic settings. Other approximations of those use the linear models, which are easy to formulate but are less accurate. And ultimately, the problem itself is ill-posed because we are acquiring far fewer measurements than we have unknowns to reconstruct. There have been other techniques that use learning-based methods, which map directly from the measurement domain to the reconstructed image domain. However, these methods require a significant amount of data to train, and they generally only work in the settings where the sensors are located and do not generalize to other settings. What we propose is an approach, or specifically learning an operator that defines the interaction between the material and the total wave field that exists in the ground. And we call this a Born Fourier neural operator. We call it Born because it's inspired by the iterative Born approximation for Lippmann-Schwinger's equations. Ultimately, what we do is we modify the Fourier neural operator architecture so that we limit it to the convolutional setting, along with several fully connected layers after that. But what we specifically do is basically we restrict the parameters in all of these modules to be tied across the different layers. And so given the incident wave field at the input, and an estimate of the material structure as well, we're able to estimate the total wave field as an output. Then we also employ an autoencoder to learn a prior distribution on the images that we want to reconstruct, and then solve for the latent space variables that are in the latent space of the autoencoder that synthesize or that can generate material permittivity F that once it interacts with the incident wave field that we know should predict the total wave field at the sampled locations. And so this is the setting that we generate. We also use GPR-Max to synthesize basically our training data set of example structures. We have a 3-layer ground structure with 2 targets inside these structures that are randomly distributed throughout the second and third layers. And we train our model using the synthetic data set, and then we test on 50 test samples that are not observed in the synthetic data set. What we observe is that comparing our born FNO to the classical FNO, that would be the classical FNO is this dashed blue line, we see that as we increase the number of layers in our born FNO, then our test accuracy improves for predicting the wave fields. And also, as we increase the number of layers in the born FNO, we see that at some point the performance saturates. And so we end up setting our computational framework so that we solve for the latent space variables Z, as I said, by incorporating the decoder component of the autoencoder. And by solving for Z, we restrict the search space for the target permittivity distribution. And as a result, we reduce the ill-posedness of the problem itself. We show over here some example results. So the bottom row is the ground truth images. The row above it is our proposed approach, which combines both the total variation and the autoencoder method. And then we compare that with the born FNO using total variation as regularization by itself, and then born FNO, the inversion net approach, which uses a convolutional neural network. And we see that the mean square error is lowest for our method. And finally, I want to conclude by summarizing that our contribution incorporates or combines both a physics-inspired machine learning or neural network approach, along with a deep autoencoder to restrict the search space of solutions. And we demonstrated that our approach outperforms other methods on the synthetic dataset. Thank you very much for listening.